Okay, so hello everyone. This is week 4 assignment solutions of the functional analysis course on nptel. Okay, so we'll start. So question number 1: which of the following statements are true? The space C naught naught is not closed in any Banach space which contains it. Then the space C naught naught is dense in all the spaces LP, P from 1 to infinity including infinity. The third one says the space L1 is nowhere dense in L2. Okay. Second option, we had already seen in the last time that for P1 to infinity, C naught naught is dense, but for L infinity, C naught naught is not dense. In fact, C naught naught's closure is equals to C naught in infinity. Okay, so the second option is wrong. Okay, and for the third option, we know that C naught naught is dense in L2, and C naught naught is contained in L1 also, which is contained in L2. Hence, L1 also is dense in L2. So the third option is also wrong. So first option we have to prove why the first option is correct. Okay. First option says that C naught naught cannot be closed. Cannot is not closed in any Banach space which contains it. So simply C naught naught, if suppose a Banach space contains C naught naught and C naught naught is closed in that space, then that means C naught naught itself will be a Banach space. Right? Any closed subspace of a Banach space is Banach space. So we just have to prove that C naught naught cannot be a Banach space with respect to any norm. Okay. So we'll use the Bayes category theorem here. Since C naught naught has a denumerable basis, which is of all ej's defined by ej of I. It's 1 for I equals to j, 0 otherwise. So this is a countable basis, countable infinite basis of C naught naught. Hence, by Bayes category theorem, like you can here you can write C naught naught as a union of okay. I'll write the space as Zn for the moment and going from 1 to infinity, where Zn is span of E1 through En. Okay. So now each Zn is a finite dimensional subspace, hence closed. Now you are writing a Banach space as a union of nowhere dense subsets. Okay, because being a finite dimensional space, proper subspace of vector space C naught naught Zn interior, like closure is itself, Zn closure interior is empty. So, but by Bayes category theorem, this is not possible. Okay, that means C naught naught cannot be complete. It ultimately means C naught naught cannot be closed in any Banach space. Okay, the first option is correct. For the second question says which of the following statements are true? The space P phi of all polynomials of degree less than or equal to phi in one variable is nowhere dense in C01. Okay. First of all, the meaning of nowhere dense is like last question also we have seen that Okay, a subset, suppose C of X is said to be nowhere dense in X if interior of C closure is empty. Okay, this is the basic definition. So here, if you think about P5, it's a finite dimensional space since it is a set of all polynomials of degree less than or equal to 1. Okay, that means it is closed, and for every proper subspace there is a result actually. For every proper subspace V of vector space X, V interior is empty. Okay, no proper subspace can have a non-empty interior. Okay, so that's why here it implies the P5 has, which implies P5 closure interior is empty. Right? That means it's nowhere dense. Okay. Second is the space C naught naught is nowhere dense in C naught, but that's wrong. In the first assignment, I think first assignment we have seen that the C naught naught's closure is C naught in infinity now. Okay. This is wrong because C naught naught's closure is equal to C naught. Okay. Third one says the set of all singular matrices is nowhere dense in M and over R. Okay. So I'll call the set S to be set of all matrices M belongs to M n over R, such that determinant of A is 0. Okay, the claim we have to check whether this set is nowhere dense or not. Okay. First of all, if you consider the mapping phi from Mn over R to R given by phi of A equals to determinant of A, then you know phi is continuous. Phi is continuous and S is basically phi inverse of singleton 0, which means S is closed. Okay, so the claim for nowhere dense is what? Claim for nowhere dense is like possible claim. We don't know whether it's true or not, but we're just looking. Is S closures interior should be empty, right? Then only we'll say that S is nowhere dense. Okay, so we are checking what are happening. So right now what we got is S closure is equals to S. So we just have to check whether S interior is empty or not. Okay, but there is a result. It says that for any topological vector space X, a subset S is S interior is empty if and only if S complement is dense. Okay, is that correct? Yes. Okay, now but if you use this result, we just have to prove that S complement is dense in M and over R. But what is S complement? S complement is set of all invertible matrices. And in the week third, I mean the last assignment session, we have seen that the set of all invertible matrices is dense in M and over R. how we have done that, like if for any A belongs to M over R, okay, we have chosen a sequence of matrices AN to be A minus 1 by n I, okay, such that where n belongs to natural number minus a set, this set, the set of all minus of lambda, suppose set of all minus lambda where lambda belongs to eigenvalues of A. Okay, so I'm doing this thing, this n minus this thing, because in order to like have this ANs, so, eigenvalues of ANs are all non-zero. Because what are the eigenvalues of AN? Eigenvalues of AN are lambda minus 1 by n, where lambda belongs to eigenvalues of A. So in order to make sure that this is non-zero, I am subtracting this set from natural numbers. Okay. So this AN will converge to A, and AN are all invertible, which means set of all invertible matrices is dense in Mn over R. Okay, which proves our current claim that which implies S interior is empty. It implies set of all singular matrices is nowhere dense in Mn over R. Okay, this is correct. Okay, is it okay? You are having any doubt? Okay.
Sir, no, sir.
Okay, thanks.
Okay, sir.
Next, I'll go to question number third. We be a Banach space, and we can write the Banach space as direct product decomposition of two closed subspaces. Now we define the projection map from V onto W with respect to the decomposition. Which of the following statements are true? Okay. So how is this mapping defined? For any x belongs to V. Yeah, for any x belongs to V, you can write x as W plus Z uniquely, where W belongs to capital W and Z belongs to capital Z. This is the decomposition we have, where W and Z are both closed subspaces. Okay. So for this x, we define the mapping Px to be equals to W. This is the projection map P from V onto W. This is linear by definition. So this is linear onto W. We want to check if this is continuous and what will be its norm. So for continuity, see, we'll use the closed graph theorem. Okay. Graph theorem which basically says, okay, let x and y be two Banach spaces and t from x to y be linear onto then graph of t is closed implies t is continuous. Okay. Oh, I guess ontoness is also not required. Yeah. Just a linear map. If to the x and y are Banach spaces, you just need a linear map. Then the graph T is closed implies T is continuous. Okay. Anyways, we have the our function P is onto here. Yeah. So we will just check whether this for P that G of P is closed or not. This is our question. Okay. If G of P is closed, then T will be continuous. What do you mean by G of P? We will take a sequence in G of P. Suppose xn, comma pxn. Okay. It converges to suppose x comma y belongs to v cross w. Okay. So xn you can write as vn plus wn plus zn. Wn belongs to capital W, Zn belongs to capital Z, for all n belongs to natural number, and x you can write as W plus Z, y you can write as suppose W dash plus Z dash. Okay. So what do you have is xn comma pxn. Pxn will be wn. Okay. Converges to W. Uh, yeah, this is converging to x comma y. Correct? Okay. Which implies xn converges to x and wn converges to y. That means xn minus wn converges to x minus y, right? But xn minus wn is zn, which belongs to capital Z, which is closed, which implies x minus y belongs to Z, correct? Okay. X minus y belongs to Z, which implies now I can write x as y plus x minus y. Okay, where yeah, since y is the limit of wn's, which are all belongs to capital W, which is closed, it implies capital Y belongs to W, right? Capital Y is in W, and x minus y we have just proved is in Z. This is the decomposition of x in the direct sum W and Z, W and Z, which implies what will be Px? Px will be equals to Y. Okay. So see, we have started with x and y, and it converges to xy. Again, x comma y belongs to graph of P because y equals to Px, which means J of P is closed. That means T is continuous. So T is continuous. Okay, no, not T. We had P here. So P is continuous, but we need to show what we need to find what will be its norm, like less equal 1 or greater equal 1. But you can observe here that P square will be equals to P. It's a projection. P square equals to P, and we know norm of P square is less equal norm P whole square, which implies norm P is less equal norm P squared. But if you solve it, it implies norm P times norm P minus 1 greater equal 0. It implies norm P greater equal 1. Okay. So P is continuous and norm P greater equal 1. Option number 3. Okay. So question number 4. Which of the following statements are true? The space C naught is complemented in the space C. Okay. Okay, now I'm defining a functional phi from C to R given as phi of any element xn. Like every element of C is a sequence, convergent sequence. So phi of xn as limit as n going to infinity xn. This is well defined because every sequence is convergent. Then C naught is just phi inverse of singleton 0. Here phi is continuous, phi is linear, linear it is enough. Okay. So here phi is a linear functional. Hence, and what do you have is C naught is, yeah, C naught is simply phi inverse of 0, right? And you know that every null space, null space of a linear functional is a hyperspace, right? Which implies C naught is hyperspace. Which implies codimension of C naught is 1. So as sir also explained in the lectures, if the codimension is finite, then uh, what do you say? The space is complemented. Okay, codimension is finite, which is 1, and the space is complemented. And the dimension of any algebraic complement of C0 is unitary. Right now, we have shown that there is a linear function, which implies C0 is hyperspace, and that follows. Third one, okay, Z is given a subspace of R3. We want to find what is the dimension of Z perp. Okay, here the G perp is not the orthogonal complement which usually represented like this. It is the set of all functionals. F belongs to R3 star, I call it, linear functionals, continuous linear functionals, such that f at x, y, z is equals to 0 for all x, y, z belongs to capital Z. Okay, this is Z per third option. Okay. So suppose let f belongs to Z perp. We know that every linear functional on R3 which has some form, particular form. F of x, y, z will be written as alpha 1x plus alpha 2y plus alpha 3z. Okay, like there exists some alpha 1, alpha 2, alpha 3 belongs to R. Yeah, this is, I mean, representation of any linear function on R3 simply. Okay, now we want that f belongs to, if f belongs to Z perp, then alpha 1x plus alpha 2y plus alpha 3 times z can be written as minus x minus y. It should be equals to 0 because in Z we have the property x plus y plus z equals to 0, and f belongs to Z perp means f at every point x, y, or z should be equals to 0. So I'm just putting that. So this should happen for all x comma y belongs to R. So if I just simplify this a little bit, alpha 1 minus alpha 3 x plus alpha 2 minus alpha 3 y equals to 0. This should happen for all x comma y belongs to R. So if I put x equals to 1 equals to y, this should imply alpha 1 minus alpha 3 plus alpha 2 minus alpha 3 is 0. This implies alpha 1 plus alpha 2 equals to 2 times alpha 3. Okay, keep it aside. Suppose I put alpha x is 1 and y is minus 1. This will imply alpha 1 minus alpha 3 minus alpha 2 plus alpha 3 is 0, which implies alpha 1 equals to alpha 2. Yeah, and from here it will also implies alpha 3 is also equals to alpha 1. Okay, so that implies f at x, y, z will be given as alpha times x plus y plus z. Okay, where alpha is just alpha 1, alpha 2, alpha 3. Okay, so what that means, this is equals to alpha times some h of x y z. Okay, this is also linear function defined as h also is a linear functional on R3 given as h of x y z equal to x plus y plus z. Okay, which means G perp is just span of h, one linear function only. That means dimension of Z perp is 1. This is wrong. It's saying dimension is 2. In fact, for any finite dimensional space, let X be a finite dimensional space and G be subspace of be a subset subspace of X, then dimensions of G plus dimension of G perp will be equals to dimension of X. This is the basic result theorem actually. So you can use this theorem everywhere. Here also dimension of dimension of Z was 2 and the dimension of the whole vector space is 3. Hence dimension of Z perp has to be 1. So we can directly discard this option using this theorem. The proof of this theorem is also very simple. Like you just take basis of x, suppose u1, u2 to un. I'm assuming the dimension of x to be n. If this is the basis, then define the coordinate functionals fj's as fj of ui is 1, then I equals to j, otherwise 0. Okay. First of all, while taking the dimension basis of x, okay, I have to let script be u1 through uk be basis of z, then extend it to basis of vector space. Okay. Then define this coordinate functionals. Now you can verify this thing. Claim is functional set of all fj j greater equal k, not equal, j strictly greater than k forms basis for G path. Okay, so this is an easy claim, you can verify. We'll go to the next question. Okay. Let V be a Banach space, and for each positive integer n, Pn belongs to L of V. Be such that Pnx goes to x for every x. Which of the following statements are true? Okay. So what we are given is Pn is a sequence of linear operator, continuous linear operators on V. Such that Pnx converges to x for all x belongs to V. Which also means that Pnx is bounded for all x belongs to V, right? So by okay, yeah. So by uniform boundedness principle, since V is a Banach space, by uniform boundedness principle, we straight away get that the norm Pn is also bounded. Hence, the first option, if this C says that norm Pn is less than C for a gen. Okay. Second option need not be true in general. We don't have enough data for that, which will be, kind of explained by option number C. Okay. So, like for option number C, we have a more general result. Okay. We say that suppose let X and Y be nonlinear spaces, and you take a sequence of operators an belongs to linear sequence of continuous linear operator an from X to Y, okay, such that anx converges for all x belongs to capital X. Okay. Then if you define a linear operator A from X to Y given as Ax equals to limit as n going to infinity Anx. Okay. Then this A will also be continuous. A is also belongs to X linear operator, continuous linear operator from X comma Y, and norm of A will be less equal limit infimum of norm of A. This is the result. This you can prove easily, not a big deal. Now we'll apply this result here. Uh, since we have the sequence of operators Pn and we have Pn x converges to x. That means my operator identity will be given like this: I of x equals to limit as n going to infinity Pn x. Hence, norm of the identity operator will be less equal limin for norm Pn, right? But identity operator has norm 1, which implies 1 is less equal limin of norm Pn. But we know that there exists a sequence which converges to limin, right? Subsequence for every sequence, which implies there exists nk such that limit as k going to infinity norm Pnk equals to limin of norm Pn. Correct. That implies there 1 is less equal limit as k going to infinity norm Pnk. This is we wanted. Okay. So it proves the third one, and second one need not be true. I tried for an example to get a sequence of operators Pn so that Pnx goes to x for every x, but norm Pn doesn't go to 1 and then goes to infinity, but I couldn't find right now. But this is not necessary. I'll try to find an example, maybe in next session I'll do. From the data given here, we cannot say that norm Pn will go to 1 necessarily. Okay. Then there was question number 6. Let C naught naught be equipped with the infinity norm, and you define an operator T from C naught naught to C naught naught, okay, by Txi is xi by I. I mean simply this operator maps x1, x2 to xn, suppose, because it's in C naught naught, maps to x1, x2 by 2, x3 by 3, like this, xn by n, then 0. Okay. So what can we say about its norm? Okay. So it is norm of Tx, okay, infinity, which is supremum of modulus of xi upon I. 1 less equal I less equal n. But you know this is less equal supremum of modulus of xi. This is simply norm x infinity. Norm tx is less equal norm x infinity. This is happening for all x belongs to C naught naught, which implies t is continuous. But is it a bijection? Yes. You take any y belongs to C naught naught. Okay. Y will be like this: y1, y2, suppose yn, and then 0. Okay. So we need a pre-image of this y onto this map, right? So we define x C naught naught as y1 2 times y2 3 times y3 to n times yn 0. Okay. So this implies what will be tx? Tx will be simply y1 2y2 by 2, which is y2, 3y3 by 3, which is y3. Simply we'll get the whole y, which implies t is onto. Okay. So t is continuous, t is onto. Okay, I haven't proved whether t is 1 1. You can simply say see t is 1 1 because tx is 0 implies x is also 0. Okay, so t is 1 1 onto continuous bijection, but is it homeomorphism? Sorry, I mean that means isomorphism here. So is t an isomorphism? Why? Because if you consider the inverse map given by t inverse of any element y, uh, okay, y at j I'll define will be equals to j times y at j, like how we found here. Y1 goes to y1, y2 goes to 2 times y2, yn goes to n times yn, right? This will be the inverse match, inverse image. Okay. So, but the claim is this is not continuous, this mapping. Why? Because you take EIs, suppose belongs to C naught naught, like which are ith component 1, all other are 0, then norm of EI will be 1 for all I, but what is norm of, like what will be T inverse of EI? T inverse of EI will be I times EI, right? Which implies norm of T inverse of EI will be equals to I. And we cannot get there doesn't exist any C positive such that norm of T inverse of EI is less equal C times norm EI, because norm T inverse of EI goes to infinity as I goes to infinity. This is not possible, hence T inverse is not continuous. Which implies T is not isomorphism. Question number 6. Then we go to question number 7. So if V is L1 and C naught is considered as subspace of V, then C naught not perp is L1. So in the class, sir has explained that if you take suppose Y as a subspace of vector space X, then Y perp will be equals to Y closure. Okay. teacher has explained. So here we are taking C naught not as subspace of L1, C naught not subspace of L1, which means C naught not per will be equals to C naught not closure, which is whole L1, because C naught not perp is dense. Yeah. The first option is correct, but in second option, you see C naught not is not the taken as a subspace of V, it's taken as a subspace of V star. I mean, not just a subspace of V star, it is kind of identified as a subspace of V star, because V star is simply L infinity. The first option was wrong. For second option, our V is L1. So V star will be what here? We know that V star is like isomorphic with L infinity, but it's not directly L infinity. V star is a collection of functionals. But you can write it as V star will be set of all Fy's. Okay. Set of all functionals where Y belongs to L infinity. Okay, and what is this Fy's? Fy's are defined as Fy's are linear functionals from V to R given as Fy of x equals to summation xj yj. So every linear functional on L1 will be of this type. That's what it means when we say V star is equals to L infinity. Okay. So when we identify C naught naught as a subspace of V star, which means C naught naught is collection of all collection of all such Fy's where Y is in C naught naught. Okay. This is how we identify C naught naught in V star. Okay. So now think of C naught naught perp. C naught naught perp will be set of all x belongs to L1 such that Fy at x equals to 0 for all y belongs to C naught naught. Okay. Which means summation xj yj equals to 0 for all y belongs to C naught naught. So one by one, if you take ej's, the numerable basis of C naught naught in place of y, okay, implies summation xj into ei at j going from 1 to infinity is 0, which means xj is equals to 0. This is happening, okay, not xj, xi for all I belongs to natural number. Because ej's are defined like that. Only at I equals to j it's 1, otherwise it's 0. So straight away you'll get xj is 0. So xi is 0. This is happening for all I belongs to natural number. This implies x is 0. Which means C naught naught perp is just singleton 0. So what is C naught naught? Which implies C naught naught perp will be set of all functionals now f from V to R such that f at 0 is 0. But this is always true. Every linear function will be like this. So C naught naught perp will be equals to whole V star, which is kind of isomorphic to L infinity. Hence C naught naught perp is L infinity. This is true. Okay. So the third option, which says if V equals to L infinity and C naught naught is considered as subspace of V, then C naught naught perp is L infinity. Okay. Yeah, here C naught naught is taken as a subspace of vector space V, right? So C naught not perp, C naught not perp you know which is C naught not's closure, right? Because it's taken as a subspace of vector space. And you know in infinity norm C naught not's closure is C naught only. This properly contained in infinity. Yes, the third option is wrong. Okay, I hope this is clear. Question number 7. Now we'll go to question number 8. For f belongs to C01, define norm f2 as integral 0 to 1 modulus of ft square dt. It's just two norm of the every function. So first of all, we are taking v to be with supremum norm C01 and w to be C01 with two norm. Now, which of the following statements are true? The identity map is continuous from v onto w. So the identity map, I call it like ID. First, if you take from v to w, okay. So if it's continuous, then what do you have? Norm x, w norm. W norm is 2 norm should be less equal some constant c times norm x v norm, which is infinite norm. Right? This should happen for all x belongs to v. I mean simply c0. Right? If identity map from v to w was continuous, right? So let's see if that's true. What is norm x2? X means I will write f here because it's functional. So it's a function. So norm f2 is integral 0 to 1 modulus of ft squared dt raised to 1 by 2, which is this is less equal integral 0 to 1 uh, integral 0 to 1 norm f infinity dt, because every uh, quantity is less equal norm f infinity, which implies norm f2 is less equal norm f infinity into integral of 0 to 1 dt, which is 1. So that's all. Norm f2. So what we got what we wanted. Hence the identity map is continuous from v onto w. But the identity map is isomorphism. For that you need the inverse image also. Identity map should be continuous from w to v. Okay. But like there are two ways to think about this. One is you know that C01 supremum norm is a Banach space, but the same space with the two norm is not a Banach space. So it cannot be isomorphism. Otherwise, it's a contradiction. One is Banach, other is not Banach. So it cannot be an isomorphism. But we'll see in another way also. Like consider the identity map from W to V now. In order for the identity map to become an isomorphism, this also should be continuous. Should be continuous. But let's see. Continuous means for all f we okay norm infinity should be less than c times norm f2. This should happen for all f belongs to c. I mean w. Yeah, w is the space with two norm. This should happen, right? But if you take sequence, suppose fn x equals to x raised to n. Let's see what happens. Then what is norm fn infinity is 1, but norm fn 2 is equals to integral 0 to 1 x raised to 2n dt whole raised to 1 by 2. This is equals to x raised to 2n plus 1 by 2n plus 1. Okay, 1 by 1 upon 2n plus 1. Okay, whole raised to 1 by 2. Yeah, so simply norm of fn 2 norm is 1 by square root of 2n plus 1. So, but you see, 1 should be less equal c times 1 by square root of 2n plus 1. This should happen for all n belongs to natural number. This is not possible because this is going to 0 as in going to infinity. Hence, identity map is not continuous from W to V, hence it's not a isomorphism. Okay, and the space W, and hence we can also imply the space is not complete. Okay, because it's a consequence of an open mapping theorem. Like if there are two Banach spaces, suppose, I mean same space with two different norms, um, uh, like if they are complete, if both are Banach spaces and we have one norm is less equal some c times other norm, then by open mapping theorem the two norms will be equivalent. Okay, then if that's the case, then the identity map will be continuous from the both sides isomorphism. But that's not true, hence W cannot be Banach space complete. Same things are also explained in open mapping theorem lecture video. Okay, so question number 9. So let V and W be Banach spaces and T be a linear operator from V to W. Map T is said to be bounded below if there exists a constant C such that norm Tx with W greater or equal C times norm X with V. The first option asks whether if T is bounded below, then range space is a Banach space or not. Okay. So for range space, we know it's a subspace of W or V or W, where W is Banach space given. So for range space to be Banach space, we is enough to prove that range space of T is closed. Okay. So let's take a sequence from the range space. Let Yn belongs to range space of T for all n belongs to natural number, and Yn converges to Y, which belongs to W. So which means what is Yn? Yn is equal to simply T of xn for some xn belongs to V. So Yn is convergent implies Yn is Cauchy also, which implies there exists capital N belongs to natural numbers such that norm of Yn minus Ym is less than epsilon for all n comma m greater or equal capital N, which means norm of T of xn minus xm is less than epsilon. But since T is bounded below, norm of xn minus xm less equal c times, okay, no, we know this thing. C times norm xn minus xm is less equal norm of T of xn minus xm less than epsilon, which implies simply the xn is Cauchy in V, and V is Banach. V Banach implies xn converges, say xn converges to x, then continuity of T implies Txn, which is Yn converges to Tx. Okay, and a sequence can converge to at most one point, hence Tx is equals to Y, which implies range space of T is closed subspace of a Banach space, hence Banach. Okay, so the first one is true. Second, Z equals to null space of T if you define. Okay, first of all, the claim is for any bounded below operator, the null space is singleton zero. Okay, like null space means what? Suppose X belongs to null space of T, then what do you know? Tx is zero, implies norm Tx is zero. implies norm C times norm x v less equal 0, which implies norm x is 0, implies x is 0. So null space is singleton 0, means whenever you take a quotient by singleton 0, this is nothing but v only, right? So then T tilde will be just a map from V to range space of T, like same map. Actually, T tilde is same as T. Its codomain is taken as range space of T. Nothing, no difference. Tilde will be well defined as well. And since T is 1 1 and onto range space of T, yeah, it's an isomorphism. Okay? I mean, it's a bijection from two Banach spaces. So from open mapping theorem, it's an open map, which implies it's a bijection. So third is also true. Okay. The last question. Let V be a Banach space, W be a non-zero closed and proper subspace. We define pi to be a map from V to V quotient W by pi of x equals x plus W. Which of the following statements are true? The map pi is injective. Okay, so since W is not a zero subspace, which implies pi cannot be injective. Like injective means what? For any x belongs to V, pi x equals to x plus W. Injective means if you assume that pi x is 0, 0 means W. And 0 element of the vector space V quotient W, which is W, which implies we know x belongs to W, right? Which is not equal to singleton 0, right? Which implies the null space of the operator pi is W. Hence it's not an injective map, okay? Because it has a non-zero null space. The map pi is surjective. Yeah, it's definitely surjective because V quotient W is the set of all x plus W's and where x belongs to V. So it's surjective. The map pi is an open map. Okay. So here, uh, what you need is if V Banach and W closed subspace, then V quotient W is Banach. Okay. Hence here we have defined a map pi from a Banach space onto a Banach space continuous linear and okay continuous linear. This will imply pi is an open map because of open mapping theorem. It's a straightaway statement. Okay. So the option number C is also correct. Yeah. Okay, so with this the assignment fourth is finished. So if you have any doubts, you can ask.
Sir, I have no doubt, sir.
Okay, okay.
Sir, send me, sir, your mail ID, sir.
My mail ID. Okay, I'll mention it in the chat box.
Sir,
Just a minute.
mention.